Yeah, you want to
full on
adjust the gain. And presumably you can mute the speaker. Okay.
Sorry.
Anticipation. It's like there's 5 minutes. Is that clock right? What? All right, let's give it a couple of minutes. As you were. Okay, the clock is caught up with us, so I'm going to get started. Let me just start where we ended up last time, talking about rapidity and pseudo-rapidity. So we had rapidity. By the way, someone mentioned my handwriting got smaller as the lecture went on, so please remind me if I'm writing things that you can't read it, and I'll try to write bigger.
Can you switch the light on?
Switch the light on.
The light on.
Thank you.
Do it again?
No. Turn it on.
It's already on. Yeah.
Right, okay. Rapidity is called y, and it's defined as half of the log of e plus pz over e minus pz. This is a kinematical quantity. Meaning it's determined by the kinematics, by the form momentum. In contrast, pseudo-rapidity we call eta, which is defined as the log of the cotangent of the polar angle divided by 2. This is a geometric quantity. That is, there's a one-to-one correspondence between an angle and the detector, part of the geometry, and what we mean by pseudo-rapidity. So the experiments like to talk about pseudo-rapidity because they, it means something very precise in terms of their experiment. This is differences, can't spell today, in y are boost invariant. So this is exactly true. If you take the difference in rapidity between any two momenta, that difference will be the same no matter how much boost we give it in the z direction, the longitudinal direction along the beamline. We want this property so that we can measure rapidity differences, and it doesn't care about how much the center of mass energy of the partonic collision was translated with respect to the center of mass of the proton collision, which is always in the same place. And pseudo-rapidity reduces to rapidity for massless particles. So most of the particles we see are essentially massless, electrons, pions, protons, and so on, Things that aren't massless are things like top quarks and Higgs bosons and jets. And jets, people often use pseudo-rapidity, even though there's actually can be a significant difference between rapidity and pseudo-rapidity. So just keep in mind that most of the time we use pseudo-rapidity, and it's not exactly boost invariant, and the real thing that's boost invariant is rapidity, which you can use sometimes. Yeah?
I remember hearing in terms of the diphoton recently, they were talking about how they could possibly measure the protons that were broken up after a collision or something. So is it possible to measure the protons that went through, or the remnants of a proton after a hard process, to use that to reconstruct the entire event?
Not really. So part of the problem is that we lose most of the proton down the beam line. Well, here's an example of a detector. I wanted to mention, someone asked about LHCb. I'll discuss it in a second, but basically this is one of the detectors. So the beam comes in here, and the collision is over here, and then most of the time, remember it has 13 TeV of energy, so most of it just smashes through and goes down the beam. So it's not what we call a 4-pi detector. It's almost, but it only goes down, so this goes down to rapidities of 4.9. Right, so it really the beam is a rapidity of infinity, but it's a logarithmic scale, pseudo-rapidity of infinity. So it's a logarithmic scale, so you actually get pretty far, and you can see from this picture that 4.9 is down to around here. Remember last time I told you that pseudo-rapidity of 2.5 is 10 degrees, which is, well, this thing covers 1.9 to 4.9. So this is pseudo-rapidity of 1.9, and this is pseudo-rapidity of 4.9.
But if we built like a better detector, repeater detector, is it in principle possible to measure the protons?
No, because there's a beam there, and you have to...
But if you keep going more and more and more, make the beam thinner and thinner and thinner, at some point you could do it. But
No, you really can't, because the beam is there. You can't cut into it. So there's this... But besides the fact it's not interesting, there's, most of the time you just get the explosion down the beam, and it's not, the decay products aren't... There's nothing special about them, and there's just... It goes down, so... I don't know what to say. You can do, if you went at very low luminosity, just collided two particles, you can in principle measure everything without a beam, but that's hard to do too. So I don't know what you're referring to with the diphotons. Sometimes the proton remnants, which is the stuff that goes kind of close to the beam that you might measure, tell you something interesting. But most of the time we are not interested in that physics because it's very hard to measure, and the detector generally doesn't have as good coverage in the very forward region as it does in the central region. Right, so this is LHCb. It's designed to study B mesons, and I'll talk about B mesons maybe today, but certainly next time, tomorrow. It's a funny detector because it starts over here, so it only covers actually 4% of the sphere, right? Which seems like you're throwing out almost all of the information. But most of the time when you produce B mesons, you have, what happens is one of the partons in the proton has much, much more energy than the other. And that's just the kinematics of producing a very light thing from gluons. The standard process for producing Bs is gluon comes in, something like that, and then it fragments to BB bar. And if you're interested in studying Bs, these B mesons, this thing happens to have low energy, so you have very low X's compared to 13 TeV to get a B meson of 5 GeV or say 10 GeV. The X's are of order, 10 to the minus 3, something like that. And so you have one is 10 to the minus 3 and one is 10 to the minus 4, and then this thing has a boost factor of 10 in the beam direction, and it'll go almost entirely forward. So when you have light stuff produced, almost generically, it goes in the forward direction. And so even though this detector only covers 4% of the surface of a sphere, it gets 40% of the Bs that are produced. Now, of course, it would be better to have a detector that covered everything, but it's a cost-benefit analysis, and they realized that they can get away with a detector that was much, much smaller than things like Atlas and CMS and still study the majority of the physics of interest in B physics. Compared to producing it through a Z? Yeah, the Z is very heavy. Or a gamma star. Yeah, because gluons, the proton's made of gluons. So you have a lot more gluons. Anything with photons or Zs are electroweak, so you're generally suppressed by a factor of 100 at least compared to QCD processes, which are generally order 1. Right? The strong coupling is large at GeV scales where this is all going on. So this process is much, much larger than electroweak processes. There is also a contribution, sure, from QQ bar to photon to BB bar. But I don't know. I would say this is a factor of 1,000 less than this. Anyway, so LHCb, there's some interesting results, mostly used to study precision properties of B mesons, rare decays, things like that, different rare branching ratios. It runs generally at low luminosity. So one thing LHCb needs is a very good vertex detector. So we'll talk about this a little bit more, but a property of a B meson is that it has a lifetime that is not too large and not too small. So it doesn't decay immediately. It decays after moving a little bit in the detector. So typical, I think I have a slide about this. So typically the way you find a B meson, well, this is, yeah. So what happens here, that PV is called the primary vertex. That's where the protons collided. And you might have produced a B bar S sub S there, which is a B meson with a strange quark in it. So it's a B bar S bound state. And then what happened is that moved off and decayed at the end of that blue arrow. And that's called the SV, the secondary vertex. So to find that it's a B, you look for a difference between where the purple dot is and the end of the blue arrow. And then what happened here is it produced a D sub S, which is a charmed meson. And the charm also has a lifetime, which is long enough so it actually lasted longer than the B meson. And so over here, and this is called the tertiary vertex. And then that decayed to a pion and two kaons. And all this drawing on top, if you throw away the drawing, what's actually seen are these purple and gray lines. So those are seen from the silicon in the tracker. And what they look for are the deposit of charged tracks. So charged particles move along, and the silicon pixels see the location of these particles. And do that, they can reconstruct the difference between the primary, secondary, and tertiary vertex and reconstruct the event. This doesn't work so well when there's 10 to the 34 protons, or what do we say, 1 billion protons colliding per second. It's helpful to have 100 million instead. And so by lowering the luminosity, it's actually easier to resolve these tracks and do this kind of B tagging. So here's an example. People were asking about how we tell the secondary vertex. This is the typical event at the LHC at current running conditions. So what's going on here is this is a beam of protons colliding. This is one collision of one bunch, one proton bunch. Remember, there's 10 to the 11 protons in a bunch. We have around 100 collisions per bunch crossing. This is what 100 collisions look like. What it looks like is each of these yellow dots represents a collision. And so the silicon in the inner tracker, what it's designed to do is measure all these tracks, and you can see some of the lines point to this point, some of the lines point to this point, some of the lines point to this point. It's a little easier for the experiment to do in 3 dimensions. In 2 dimensions, it kind of seems like a mess. But they're actually pretty good at resolving which particles came from which vertex. I mean, it's impressive, but you see you need very, very good resolution. And that's why these incredible detectors have such fine resolution, and they need such an expensive and detailed pixel detector very close to the beam. So what they try to do is resolve all of the interactions that they're interested in and say this one here produced a muon, right? So they might know this blue track was a muon because it went all the way through the detector out into the muon detector, and they can trace it all the way back to this interaction. So this tells you this interaction was the hard interaction that produced the thing you're interested in, and anything that came from these other collisions I don't care about. And maybe here there was something, maybe that was an electron or a photon or something, and that was maybe a slightly hard secondary collision.
You see all this in the vertex tracker?
Yeah, this is actually data. This is a picture from Atlas of their well, it's reconstructed, but it's an actual event. Yeah, right. So this is what they do. They take an event and then they do a lot of analysis on it to figure out where these tracks are and reconstruct it from the detail of the charged particles moving through.
You also need the electron weak parameter.
Well, this is a zoom in on the central region near the beam, right? The beam, this is the collision, right? This whole thing might be, I don't know, a couple of centimeters, right? And so outside of this, we're still in the central inner detector, right? And if you zoom out, you'll see everything else going on. But this is just to show you how you can resolve all the interactions. Now, of course, at very high luminosity, you can't do this anymore. And so it's a real issue as we go to the VLHC or one of these upgrades. Instead of going at, what are we at 10 hertz per nanobarn, if we went up to 1,000 hertz per nanobarn, there might be 1,000 of these, and then we wouldn't be able to do it. So it's an issue that we have to deal with. And there's been actually a lot of progress in the past 5 years or so, understanding other ways to deal with this pileup contamination other than vertexing. Yeah?
What are the lines that are not coming from the international
What are these things?
Some of the lines don't seem to be connected.
Right, like this or something? I mean, I don't know. There certainly are interactions down there, right? Protons are banging into stuff all the time. They could bang into beam gas and I don't know. And the the bunches are pretty broad, so the bunch might be this size, and it might be even longer and has a long tail, so you can have collisions that are farther away from the actual beam. Some of these you can see curvature, right? So the lower the energy of the particle, the more it curves. And you can see some of these particles curve. I don't know what's going on with that one. It's kind of funny. Okay. Anyway, yeah.
Can you say more about how the primary vertex is constructed for the case of production?
Yeah, well, I'll talk more about bees, but it's basically like this. So you say, I put tracks and they point to this, and if it was a bee, you would see another vertex over here, right? And then you look for tracks pointing to something that's not along the beam line, right? And what you look for is this impact parameter, so the transverse distance from the beam from the direction of the decay. Mm-hmm. So you'll see, I don't think we have any here, but you'll see a set of lines that converge on a point over here. And that's you tell there was some particle that had a lifetime of, a millimeter or centimeter.
Yeah, but that's how you can tell where the secondary vertex is, but how can you reconstruct the primary vertex?
Well, that's the primary vertex.
But there are no lines.
Oh, there are. I mean, it depends what happened at the collision, but usually you have other stuff produced too besides the bee.
Okay.
Yeah, right. If it's just the bee, you don't see it, but usually you produce. Yeah, because remember, even a process like this, these are bee quarks, right? And so to turn into mesons, you need to hadronize, and you pull in up quarks from somewhere else in the event, so you have other stuff. And usually there's pions produced near where the bee is produced, and so on, and you'll see tracks from those as well. Right? You rarely just produce purely a bee and a bee bar. Right. If you ran in a resonance, for example, the bee factories, what they would run is the upsilon resonance, which is something that's basically always decays into a BB bar. So they produce it on resonance, they produce one of these upsilons that would always decay to 2 bees. And then you knew exactly that you always got bees. But at the LHC, we can't do that. So you usually produce a lot of stuff. And most of the time, you don't produce bees. Right. But 1 in 1,000 events might produce a BB bar pair, or 10,000 events. Right. And you don't just produce those, you produce other stuff too. You try, but generally the bee technique is very good, right? It's a trade-off between how well you want to reconstruct bees and how well you want to remove fake bees, right? And so you choose a trade-off base. The bee technique is rather well. So we'll talk about bees later. Let me wait with that. Other questions? Okay. So what are the kinds of things we can measure at a collider? The basic thing we measure is form momentum. So what we try to do is measure as well as we can the momentum of every particle. So we try to measure the energy, the momentum in the x and y direction, which are taken transverse to the beam, and the z component of the momentum. Of course, we can't really measure all of these separately. Usually what we measure is where the particle went, which tells you an angle, theta and phi, or pseudo-rapidity, and the azimuthal angle. And we measure the energy from how much is deposited on the calorimeter. And if we know what the particle is, and we often know what it is, well, it's usually a pion, then you can determine the energy by just saying that p squared is the mass of the particle you want, which is generally 0. Sometimes you want to measure the energy and the 3 momentum separately. For example, to tell the difference between, say, a pion and a proton, which look from the experimental point of view pretty similar. Then you need to measure the energy and the momentum, and you can do that for measuring the 3 momentum from looking at the curvature of a track, and then you measure the energy from the amount of energy deposited in the calorimeter, or the way the particle slows down, or the curvature changes with time, and so on. So in principle, in some cases, you could separately measure the energy and momentum, but mostly we measure just the direction and the energy, and that tells us roughly what the form momentum is. Right. So we talk about transverse momentum. Which is a vector, which is just the x and y components of the momentum. And the nice thing about transverse momentum is it's boost invariant. It only depends on x and y, and longitudinal boosts only change pz and energy. So this is a naturally boost invariant quantity. Of course, we measure the pseudo-rapidity as well, which is pseudo-rapidity is not boost invariant, but differences in pseudo-rapidity are approximately boost invariant. As I said, and then we can measure the missing transverse momentum. PT slash, which is a vector, which is minus the sum over the particles of PT of the particles. Right? So if you had a neutrino, you would never see the neutrino, but you can infer that there's a neutrino there by adding up the 3 momentum of everything else and seeing that it didn't add up to 0. In particular, the transverse components don't add up to 0, and that means that there was something going off in this way, and by momentum conservation, something else had to be going in that way. So you can do this, and if you have one neutrino in the event, this will tell you the 2 momentum in the transverse direction of the neutrino. You can't know the longitudinal momentum of the neutrino, because if you add up the longitudinal component of all the stuff you measure, it doesn't have to add up to 0. I mean, if you measure the longitudinal measure of everything in the event, remember you can have events, you can have a collision, and things go this way and things go that way. Right? That's a typical collision. In fact, from LHCb, you know that we have to have collisions like that. So if I add up the 3 momentum of this and this, it has a net component in this direction. Right? So in general, you can't know the total boost of the event, which is why we use boost invariant stuff. On the other hand, the PT of this should be opposite the PT of this. 1 and 2. And so the PTs should add up to 0. So you can determine the transverse momentum of a missing energy, or if you had one invisible particle, you would determine its momentum. But in general, you can't determine it if there's more than one, and you can't determine the longitudinal component. We talk about missing energy, it's really missing transverse energy, which is just the magnitude of the missing momentum. So this is a word that's commonly used. It doesn't mean it's energy. It's really missing momentum, and it's not full energy. It's really transverse energy. But in general, that's what we call missing energy. People often like to talk about something called HT, which is the sum over some kind of particle. Well, let me generalize this. Some kind of objects of PT of the object J. Right? So it's some kind of scalar sum. So it's sometimes like this, or sometimes it's the sum of PTJ vector. Sometimes you add the momentum before you take the value. So there's not a unique definition of what HT is, and there's not a unique definition of what the objects are you would sum over. You might say, take the 2 hardest jets in the event, sum their momentum, and sum the transverse momentum. Right? And this gives you some measure of the activity in the event. You might take all the leptons in the event and sum their momentum. So the objects can be different things. So whenever you read about HT, just make sure you know which HT they're referring to. There's not a unique definition of it. But it turns out to be a useful observable for certain things.
Is the second definition based on missing ET?
Well, it depends on the objects are.
Oh, I see.
So usually you choose some localized object. I should say missing ET is very hard to measure because you need to know everything in the event. Right? And so you need to know not just the stuff in the central region, but the things that are forward as well, where the detector is worse. You have to really be able to reconstruct every particle. Well, if you're looking for something like Higgs to gamma gamma, you don't care about anything else. You just care about those 2 central photons that produce the Higgs boson. So process of missing ET, this is a very challenging thing to measure experimentally, and there's often a lot of experimental uncertainty on the value of missing ET. For example, 10% or 20% uncertainty on ET. Something that's hard to reconstruct. For certain kinds of events, it's easier to reconstruct. And sometimes, if you know the ET should be recoiling against, say, a single lepton, you can just say the transverse momentum of the lepton is the thing you're interested in, and use HT instead, which is local. It depends only on the objects that are well reconstructed. So there's various subtleties involved in this, which we could talk about, but maybe aren't that interesting for now. So another useful thing is the invariant mass. Mass and invariant mass. Invariant means Lorentz invariant, which is, m squared is the sum of p some objects j mu squared. So it's a Lorentz invariant quantity. So this is the thing if you summed over the 2 photons in the event and took the 4 momentum, added them together and squared it, you might see a peak at the Higgs boson mass, which would tell you there was a Higgs there. So in order to do this, you need to be able to reconstruct the full 4 momentum, or at least some approximation to it by reconstructing the angle and the energy. Okay. So those are typically some set of observables that are commonly used. So let's talk about an example process. The classic observable at the LHC is the Drell-Yan process. So Drell-Yan is hadroproduction of a lepton pair through a Z boson. So this would be protons coming in. Generally, there would be some quark within the proton and an antiquark that collide and produce a Z, and they produce a lepton pair. So you can write the cross section for this. So we talk about so the cross section for this. So what we're often interested in measuring is the mass m squared, which is the p of the electron plus the positron squared. Right. So if I measured this cross section, I might see a peak at the Z boson mass. You can measure other properties of it. You can measure just one. You can measure the electron. You can measure other things. But let's just focus on this for now. So what we're interested in calculating is d sigma dm squared. We can write this as integral over the partonic momentum fractions times d sigma hat dm squared of q cube r. So this is one of the few processes where we have a rigorous proof that this gives you the correct distribution up to corrections. So let me write plus order lambda QCD over m squared. Right, so this won't be exactly right. There'll be some small corrections to it from things like, another quark. I don't know. Some interactions from quarks within the proton and that quark, or maybe another gluon from that. And those things generally are small effects suppressed by factors of lambda QCD. So what are these? These are PDFs. This will be the PDF for a quark inside the proton, and this will be a PDF for the antiquark inside the proton. This mu is the factorization scale. So this separation is dependent on a scale choice that you make for what the PDFs are. This mu dependence cancels in the perturbatively calculable hard cross-section. Right, so these are PDFs. This is the hard partonic cross-section. So this, when we put hats on things, it means it's a partonic process. Well, if we don't have a hat, it means it's a hadronic process. So hadrons mean I collide the protons together, and parton means I'm colliding quarks together. Right. So what's going on here is these quarks have momentum. So we have the proton with momentum p mu, and we have a quark within the proton with momentum, say, q1 mu, is x1 p1 mu. You can't see? Okay. I'll draw the other one over here. How far can you see? Can you see here? Okay. So I'll not. Sorry. Okay. Well, it's not very interesting anyway. Okay. And we have the other proton here with q2 mu with a momentum fraction of the proton momentum. Remember, everything is going this way or that way, so they're directly proportional to each other, and they're both essentially massless from this point of view. So the only freedom for the quark momentum, it has to be a number times p1, and this number, these x's go from 1 if it had the full momentum to, if it's 1 GeV over 13 TeV, that's like 10 to the minus 4 or so. So x1 can vary at the LHC from 10 to the minus 4 to roughly 1. I mean, it can be even smaller, 10 to the minus 5, 10 to the minus 6, but then you're in regimes where strong interactions play a role. So what is this? So if we have this collision, then we have S hat, which is the partonic invariant mass. So S hat is Q1 plus Q2 squared, which I can expand it out is Q1 squared plus Q2 squared plus 2 Q1 dot Q2. So Q1 are the squared and Q2 squared are the masses of the partons, which are 0. And so Q1 dot Q2, this becomes 2 Q1 dot Q2, but Q1 is xp1 and Q2 is xp2. So this is 2 x1 x2 p1 dot p2. But 2 p1 dot p2 is like 2 q1 dot q2 equal to s, the invariant mass of the full collision. So this is x1 x2 times s. Right? So this says that the Bartonic invariant mass is related to the hadronic invariant mass by the product of the two momentum fractions. Right? But what is s hat? S hat is the invariant mass of these two quarks, which by Lorentz invariance, the momentum conservation, is also the invariant mass of the lepton pair. Right? So s hat equals m squared, at least at leading order. Right? At higher orders, there can be corrections from, say, a gluon emitted off of here, or something like that, which means there's not a one-to-one correspondence. Well, even s hat is not precisely well defined. It's really a quantity that's relevant for 2-to-2 processes. But let's just work at leading order. In which case, this is exact, and then s hat is m squared, and so this thing we just need to calculate d sigma hat d s hat, which depends only on this product. So that lets us simplify this cross section to d sigma d m squared is given by a luminosity function of m squared d sigma dm squared, where the luminosity, generally as a function of s hat, is given by the integral of dx1 dx2 f of x1 f of x2 times the delta function x1 x2 s minus s hat. Okay? So what this says is that to calculate the differential cross-section for Drell-Yan, I only need this single function of m squared, and then I need the perturbatively calculable cross-section as a function of m squared. That is, it doesn't depend on the PDF separately. It only depends on this combination of the product of the PDFs. Right? This is called a luminosity function. Shouldn't there be a hat somewhere? This one? This? Bottom? Here? You want a hat? This one? This? Oh, this one. Okay. Yeah, thank you. So this is nice. So luminosity functions are useful when the cross-section doesn't depend on x1 and x2 separately. It only depends on the product, which happens when you have S-channel production. So whenever I have a resonance or something like that, or you have two partons come in, produce something that then decays, that's a case where the luminosity functions are useful. And that's the majority of things we're interested in have that feature. Right? The other example is T-channel processes, where you have, well, I may have, something like this is a T-channel where I might produce, I don't know, say, WW. Right? So there's a T-channel contribution to WW production, which you couldn't determine the WW cross-section from using a luminosity function. But if I want something else, like single W production, luminosity functions would be useful. So let me show you what these look like. So here are some luminosity functions for the LHC and the Tevatron. Well, I don't know what you can get from this. Well, maybe there's a couple of things. So this is, first of all, this is the logarithmic plot. So this is a function of square root of s hat, which is the energy, this basically the center mass energy of the things that are produced, or the resonant energy. And this is the luminosity function as, well, these are luminosity functions as a function of that. So you can compare the curves, this green, blue, and red are from the Tevatron, and this green, blue, and red are from the LHC. You see clearly the LHC has larger luminosity at the same invariant mass. So that means the cross-sections are going to be bigger for producing, say, a Z boson. So where's a Z boson here? So square root of s hat in TeV. So a Z boson is around here. So this is 100 GeV. This is around 90 GeV. So is there a pointer or something? I use a mouse. Right, so if we go up from 100, So if we're interested in QQ bar, so QQ bar is down here as red. So we could compare QQ bar luminosity to QQ bar luminosity at the LHC, and you see there's about a factor of, 10 maybe, 10 times greater. So that means there's a 10 times greater cross-section for producing a Z boson at 100 GeV from the LHC of the Tevatron. On the other hand, if we look at something like a 500 GeV, or say a TeV particle produced from QQ bar is this red curve compared to this one at the LHC, and there's a factor of 100 difference. And then if you go beyond a TeV, clearly the Tevatron couldn't produce it, and so there's a factor of infinity. But basically the point is that that these give you a rough idea of how big cross-sections are for different channels. You can also see that the gluon cross-section here is much bigger. So the gluon is the green, and you see it's larger than the QQ bar cross-section. That's because the LHC is colliding two protons. So the antiquarks, there aren't that many antiquarks inside a proton, and generally in high energy, you should think of it mostly as gluons. So really the LHC is a big ball of gluons. The Tevatron is also a big ball of gluons, as you can see from the green line there as well. And I don't know what to say. So you can see at the Tevatron, the lines cross here. So where they cross, the gluon and the quarks cross at around half a TeV, and that means at a very large invariant mass, close to the machine energy, right? That means that x's have to be close to 1, right? So you're looking for something that carries an order 1 fraction of the proton momentum. Well, you know that a proton is quarks, so mostly it's 2 up quarks and a down quark, and so you expect roughly the third of the momentum to be in an up quark and a down quark. When you get to energies where you're probing x values that need a significant fraction of the momentum, they have to be in these what are called valence quarks. And so you see that for the Tevatron at least, you end up with a larger fraction of large amount of energy being in the valence quarks than in gluons. Well, at the LHC that isn't true because you have it's proton-proton, so you don't have any antiquarks to compare. So the antiquarks, which are involved in the red curve, are always much less than the quark ones, which are in the blue. So this is quark glue, this is glue glue, and that's antiquark. So I don't know, you can think about it and tell some stories about why the curves look like they are. But if you're doing an analysis, so for example, these luminosity functions were fun for people who were interested in the diphoton excess, right? As you probably half the people in this room have worked on it. We saw this, we see some little bit of an excess at 13 TeV. We didn't really see much at 8 TeV. So why is that? Well, one thing you could say is that maybe it's dominated by, you could ask which partonic processes have the property that they're not very likely to produce a 750 GeV resonance at 8 TeV, but are likely to produce one at 13 TeV. And you could do that by looking at the luminosity functions. You wouldn't want to compare LHC to Tevatron, but compare LHC at 13 TeV to LHC at 8 TeV. And you might see that there's a bigger jump in the gluon luminosity function than the QQ bar. So you'd say, well, then if I make it something that's produced from gluon fusion rather than QQ bar, it could explain why the cross-section is much larger at 13 TeV, right, rather than just scaling up the energy. So these things are fun to play with, and it's good to have a little bit of intuition and a handle on what these shapes are. Yeah?
These luminosity functions have a factorization scale dependent stuff?
Yeah, they do. And generally, this is plotted as a function where you set the factorization. So there's a mu here, and usually you set mu equal to s hat, which is the only natural scale for resonance production. So it's not much of an issue. Yeah.
So what is factorization scale, and then why does factorization dependence of factorization scale cancel out against the
So it's a great question. Can I hold off that question until we talk about QCD? So we have to define what these factorization scales are, but they're inherent in the PDF. The PDF has an x and well, I'll define PDFs and talk about the particle model and what they are, but not yet. Oh yes, the question was what is the deal with this mu in the factorization scale? How do we think about it? Why does it cancel between this and this? Tell me about factorization scales. And I said I will, but just wait. Okay. Where were we? We were doing Drell-Yan. So we had. Okay. So we have this luminosity function. So what is d sigma hat dm squared? So d sigma hat Vm squared. So we're interested in this for the process. We basically want to calculate this partonic process where we have a Z and a lepton pair and quarks. So what does this look like? We have some couplings. So this is going to be, there's a coupling here and a coupling there. Electroweak coupling, but let me just call it G. So the cross section is going to go like G squared over the propagator, which is S hat minus mz squared plus I times the width, mz squared. This is the Z boson propagator squared, which is G to the fourth over S hat minus mz squared squared what does this look like? This is a Breit-Wigner distribution. So it looks roughly like that, where it's a curve with a peak at mz. So this is d sigma ds hat, and a width of order gamma z. Let's call it gamma. Okay, so it's a standard resonance curve. Let me see if I have a lot of this. Yeah, so here's what you get. Here's the atlas data on this observable. This is Drell-Yan, so the blue is Drell-Yan, and the other colors are various backgrounds that aren't Drell-Yan but look like, but also produce a lepton pair. So this is E plus E minus. You can see there's the peak at the Z boson mass, and there's a long tail off at higher energy. It's a logarithmic plot, so it's a little hard to determine the shape, and it's logarithmic on this axis. So these backgrounds are actually very, very tiny. You know, they're down by orders of magnitude from the peak. This is one of the best measured observables at the LHC. It's very clean, and there's a nice theory prediction for it. Here's a CMS version where you can see clearly the resonance peak. So again, it's a little weird because this axis is logarithmic, but roughly the width of that is the Z boson width, and the shape is determined by the Breit-Wigner distribution. So remember the width as does anyone know the width of the Z boson? 2.5 GeV, excellent. So gamma Z is 2.5 GeV, and the mass? 91. Right. So the width is much smaller than the mass. So when the width is much smaller than mass, we can do an approximation where we take the limit that gamma goes to 0. So remember the width. So as gamma goes to 0, this becomes sharper and sharper, right? Gamma is the width of this. So I make it smaller. The peak gets higher. So you see if gamma were 0, when S equals mz, this would be infinity, right? But gamma is not 0, so it's not infinity, but it's very large when gamma is small. But you can approximate this. You can take the limit of this, and in the limit, this becomes a distribution, which is a delta function distribution. So when gamma over mz goes to 0, this reduces to g to the fourth pi So it reduces to a delta function at mz, and kind of by dimensional analysis, there has to be a factor of units of 1 over mass squared in this. And there's a factor of g to the fourth. So what does this tell us? This tells us that the well, I should say let's talk about this width at all. Why is the width so small? Well, how do you determine the width? The width you calculate from the decay of a Z. Right, so you have a Z boson decaying to various things, say E plus E minus. So you get a factor of G here, and you have to square this. So you get something that goes like the coupling squared. Right? So in general, gamma goes like the coupling squared, and the cross section goes like the coupling to the fourth. Right? So that means that when you're on resonance, when S equals mz, the whole cross section only scales like G squared instead of G to the fourth. Right? So this is useful because what also scales like G squared is the production rate. Right? If I also just look at QQ bar goes to Z, this also has a fraction of G. So this is sigma QQ bar to Z, sigma hat. Right? This goes like G squared. So really what's going on here is we get the cross-section in the limit that the width goes to 0 is given by a product of the production rate, which goes like g squared, times the decay, which then doesn't have any factors of g. So this is what's called the narrow width approximation. Which says that the sigma goes as gamma over m goes to 0, goes to the cross-section for QQ bar goes to z times the decay rate for z to say e plus e minus divided by gamma total. Well, gamma total is this gamma z, is the width of the curve, right? So this is also known as a branching ratio. Right? And the reason it's factorized in this way is because of the delta function. It says that in this limit, you have, when you're, the cross-section only has support on resonance, right? So it means you produce an on-shell z, which then decays. This is, of course, the semi-classical intuition that you produce particles and then they move along and they decay, right? And when the width is very small, it means that the lifetime is very long. So it's essentially a classical particle. And the limit width are really 0 would be stable, and you would see it, right? So it would move along. But if it's very small, it's metastable, so it moves along and then decays, right? So metastable, I mean, think of a muon, for example. You can see the muon, and then it decays. So clearly, you should be able to calculate the rate for producing a muon, and then the rate for it to decay separately. This is justified rigorously in quantum field theory through this narrow width approximation, that in the limit that the width is small, the cross-section factorizes into the production and decay, right? And this production and the decay, you get this nice cancellation of a factor of g squared from the full production rate, which goes like g to the 4th, and one factor of g squared from the particular mode. Right? This branching ratio can be of order 1. If there's only one decay mode, this is order 1, and then the rate for pp to z to e plus e minus is of order g squared, not of order g to the 4th, as you might think from the Feynman diagram. So this explains why the cross-sections are large. You can see the resonant peak there, that is actually very enhanced. So basically, the point is that if you're on resonance, the cross-section is much bigger than off resonance by a factor of roughly g squared when the width is small. So that's why we talk about branching ratios. So this is just the rigorous derivation of this factorization of production and decay. Okay. Questions about that? Narrow width approximation? We use it all the time, often without saying it. So really what it means in terms of quantum field theory is this is a probability, and this is a probability. So we're saying that the full quantum mechanical amplitude, which really has all these interference effects, factorized into something where the interference effects for this are calculated and the interference effects for this calculated, but there's no interference between these. So what would cause interference between these? Well, you might have a diagram where you would have, say, a photon coming off of this. Let me draw. So I could have a diagram where I have a photon coming off of this, crossed with, or let me say a loop. I could have a loop like this, and then I could have a loop like that, right? And in general, if you calculate the full amplitude, there's interference between these two, right? But in the narrow width approximation, that interference is negligible, right? You're saying I can calculate this squared and then multiply it by this squared, and I never have to worry about the interference between the two. Right? I don't have to add them together and then square it, which gives you the cross term. Right? And that's this semi-classical picture that the interference effects can be computed separately. And that's really what the content is of the narrow width approximation in terms of quantum field theory. It's dropping quantum mechanical interference effects between production and decay. And it's justified rigorously in the narrow width approximation, which this delta function enforces this long distance behavior. It factorizes on the on-shell amplitude.
So I still don't get why when it's off-shell and on-shell.
Oh, well, if it's off-shell, the width obviously has to be important, right? If S is not near MZ,
Okay.
right? And if this is big, if this is small, but this is not close, if this is not within the width of MZ, then you can ignore this, and then the whole thing goes like 2 to the 4th. Yeah, good question. Which again, I didn't repeat. Okay. Next, let's talk about W production. So the word Drell-Yan process, I think technically refers only to production of leptons through a resonance Z, but we often use it to talk about production through a W as well. I think it's not technically called Drell-Yan. The W is similar. The main difference is that we can't measure both of the leptons. The process is again QQ bar to W, which decays to say an electron and a neutrino. Right? So now we can't look at the invariant mass of the electron and the neutrino because we don't know the neutrino's momentum because it leaves a detector. We can reconstruct the neutrino's transverse momentum because we say, well, it's equal and opposite to the transverse momentum of the electron, but we can't get the Z component of the neutrino. Right? We have one extra degree of freedom. Of course, if we knew there was a W, we would know that the sum of the momentum of the electron and the neutrino would reconstruct the W mass. But if we're trying to, for example, measure the W mass, we clearly can't use that constraint. So we have to do things a little differently. Nevertheless, this is S-channel production, so it factorizes in terms of these luminosity functions. So the cross-section is, again, a luminosity function times the partonic cross-section. So really what we're interested in is the partonic cross-section. So we can calculate d sigma hat. This is often given in terms of this theta star variable. It's given by 3/8 of 1 plus cosine theta star squared. So theta star is the polar angle in the rest frame of the W. It's Lorentz invariant because it basically says take your event and go to the rest frame of the W. So no matter what longitudinal boost frame you're in, just Lorentz translate back to the W frame. So it's sort of trivially Lorentz invariant. So in the W rest frame, let me draw it down here. We have the electron going off this way, and the neutrino going off that way. And theta star is this scattering angle in the rest frame. So this is, we have PT is the transverse momentum, PZ is the longitudinal momentum, and the magnitude of P is this hypotenuse here. In the rest frame of the W, we know the total momentum is the W momentum. It's just MW. Then the electron momentum would have to be MW over 2, because the W just splits, and we're going to neglect the electron mass, and then there's some momentum P, and then the neutrino momentum is MW over 2 minus P. Right? So to the extent that the electron is on shell, the magnitude of P is MW over 2. So that this is light-like. So this is MW over 2. And this tells us that we can, so then so this is MW over 2. So PZ is square root of MW over 2 squared minus PT squared. And then cosine theta star, cosine is this over that, is square root of MW2 over square root minus PT squared divided by that. So we get square root of 1 minus 4 PT. Right. So, as I said, theta star is Lorentz invariant and PT is Lorentz invariant, boosted variant. So you should have a relation like this where it only depends on PT. So instead of looking at the differential cross-section in terms of theta star, we can look at the differential cross-section in terms of PT. Of course, this only works if we know what the W boson mass is, but for a given W boson mass, we can do this conversion. Okay? And this is, again, the PT of the electron. So this is the thing that's easy to calculate. You just calculate the Feynman diagrams of the W rest frame, and you get this distribution. But now we want to change variables, so this is something we can actually measure, the PT of the electron. So we want to change variables from the differential cross-section in terms of cosine theta to the differential cross-section in terms of PT. So that's easy to do because we have, this only depends on cosine theta. So we square this and we get, 1 plus this, so we get 2 minus 4 pt squared over mw. But there's another factor which comes from the Jacobian from changing from cosine theta to pt. So what do we get? I'll lift this up in a second. Okay, so we have two factors in this PT distribution. One factor, this was just the translation of the 1 plus cosine theta term, and this factor comes from the Jacobian. But notice there's an interesting feature of this, that if PT is equal to mw over 2, right, which happens when the electron is exactly transverse, if it doesn't have any z momentum, the W would have decayed in it, that is, the lab frame is the W boson rest frame, then it blows up. Okay, so that's a little weird, right? Seeing a cross-section blow up at a finite value of some parameter. In practice, the distribution won't really blow up because this assumed that we were just doing producing only electron and neutrino and nothing else. Really, there's usually a chance that the W will have some momentum itself. There's really zero chance that the W boson will have no transverse momentum at all. So usually it gets a little kick, and the singularity at PT at mw over 2 is resolved to something that's kind of smooth. So what does it look like? So here's, this is the mu on PT in W candidate events from Atlas. So what's the W mass? 80. So PT over 2, MW over 2 is 40. So we see there, instead of being infinity at MW over 2, it's finite. But so the reason there's a peak, this is the Jacobian. Which leads to something called the Jacobian peak. Right? So in the Z boson, we saw a peak due to the existence of a physical particle with a resonance. This peak is due to a change of variables. It's due to a Jacobian factor. Nevertheless, it's still a peak, and it's still useful. So one thing you could do to measure the W boson mass is just look for the peak in this distribution. Right? In fact, that's how they measure the W mass, is looking at the peak in distributions like that. Now,
how do you predict how we could pick it?
Right. So how do you pick it? You certainly don't predict it from this leading order formula. You have to go beyond that. You have to go to next leading order or next to next leading order. And so, in fact, that's one of the reasons that this is not the best way to measure the W boson mass, because the location of the peak and the height of the peak turned out to be very sensitive to higher order effects. They turned out to be sensitive to the WPT, which is something that actually, the W is very small PT of order lambda QCD that can still affect the shape of the peak. And that's something that's very hard to calculate. There's another thing that's not great about this observable, is that it only depends on the muon. And we actually know that there's more information in this because there was a neutrino, and we haven't used anything about the fact that the neutrino, we know two components of the neutrino momentum, its transverse components, and that hasn't come into play in this observable at all. So there's another observable that is commonly used to study, in fact, mostly used to study the W boson mass and to measure it, called the transverse mass. So to understand transverse mass, let's just write down the W boson mass is given by the energy of the electron plus the energy of the neutrino squared minus the transverse momentum minus the Z component of the electron. Right, this is just the definition of W when it decays to an electron and neutrino. So we know this. We don't know this. We know this. We know the transverse component of the neutrino momentum. No. And we know this. We don't know this. I'm sorry, we do know. We measure the Z component of the electron momentum. So we know this. and we don't know this. So we don't know this and this, which is why we can't just plot the invariant mass as a function and look for a peak at MW. Right. So instead of using MW, we can look at what's called the transverse mass, which is defined as E, the transverse energy where this transverse energy is defined as basically, transverse energy assumes that there is no z component, and you just compute the energy, as if pz were 0. So in particular, when pz equals 0, the transverse energy is the energy. Right. So this thing depends on the stuff that we actually know. It depends on the transverse energy of the electron and the neutrino. It depends on the transverse momentum of the electron and the neutrino. Moreover, everything in this formula is boost invariant because it depends on transverse components only. So let's get some intuition for this. Let's consider what happens when consider one when everything is transverse. Right, so that means the protons come in and everything goes perpendicular to the beam line. Right, so the electron might go here and the neutrino might go there. Right, so in this case, PZ, so these components are 0, which means the transverse energy of the electron is the energy of the electron, and the transverse energy of the neutrino is the energy of the neutrino. And then the transverse mass becomes the invariant mass, I should say. This is not necessarily MW, just M. Right? So when everything is transverse, the transverse mass reduces to the invariant mass. But of course, when there are some z components, this is not going to be true. How are we doing on time? Would I have another 15 minutes? Okay, so now we can imagine they're in the beam plane. So that means there's a plane defined by the beam direction and the production direction. So basically, we're just setting px equals 0. So everything goes in this direction. Electron and neutrino. So in this case, well, let me draw the momenta here. So we have pt, we have energy, and pz electrons. So can you read this? This eraser doesn't work great. And the neutrino momentum has equal and opposite 3 momentum to the electron momentum. So then the invariant mass is the sum of them. So this is m squared is 2e squared. And the transverse mass is E transverse plus E which is, so the transverse mass, we're dropping the electron energy, so it's just the magnitude of PT. So E, the transverse energy, is the PT. So we get 2 PT here. And this is 0, so we get 2 PT squared. 2 PT squared, which is 4 PT squared. Moreover, this energy here from this triangle is PT squared plus PZ squared. So this is 4 PT squared plus 4 PZ squared. So what this means is that the invariant mass is equal to the transverse mass plus PZ squared. In particular, the invariant mass is bigger than the transverse mass. And this is in fact always true. You can show that it's not a hard calculation, but if we're a general situation where this is rotated with respect to the beam, there's some angle dependence. But the main point is that there's a strict bound that the transverse mass is less than or equal to the invariant mass in all cases. So this is nice because it means that if there's a W boson, we should expect to see an endpoint in the transverse mass distribution at the W boson mass, right? Which is a nice kinematical feature that's helpful for measuring the mass. Okay, so given this, it's not hard to I'm just going to work over here. Now, work on this board. Okay, so what do we get for the... Well, let me not even write the formula. I'll just show you the plot. So here's the transverse mass distribution for the W boson. These are CMS measurements. This is for W plus, and that's for W minus. So remember, the W boson mass is 80 GeV, so there's an edge here, and you see the edge isn't quite there because there's higher order effects that move it. You also see a peak. This peak is again a Jacobian peak. It's due to a change of variables. It's something related to the W boson mass. I think the peak is actually at closer to MT, and you can see it here also. So this distribution has these nice features that it has both a peak and an edge, and it's actually described by it's described well by the leading order cross section, so it's less sensitive to higher order effects, and it includes information about the transverse momentum of the neutrino, which the transverse momentum of the lepton didn't include. So this is the transverse mass is what's used mostly to measure the W boson mass. It was used at the Tevatron, is also used at the LHC. You can see, or even with 200 inverse nanobarns, which is not very much data at all, they had a good resolution of the W boson, and you can see its mass from this plot. What is what? Oh, electroweak. Those are electroweak contributions. I mean, this is electroweak, but those are other electroweak contributions. Things that fake muons are just directly production, not through W. Does anyone know why this one is bigger than that one? PP Collider, so what? So what? More used than used. Right. Right. So W plus is predominantly produced from, a positively charged quarks, right? So an up and a down bar, right? And a W minus would be a down and an up bar, right? And there's twice as many ups as downs in a proton. So you expect that the one with ups should be twice as big as the one with downs. That's roughly what we're seeing here. Well, that's consistent with your kind of leading order understanding of the proton. So from this, you can tell that the proton is made up of 2 ups and a down. That's not bad. Okay, so that's transverse mass. There's generalizations of transverse mass. The basic idea behind transverse mass is you use all the information you have, and then you make a distribution that has some feature that tells you the mass of the particle that's this intermediate resonance. So this works. Transverse mass works when you have one missing energy particle, like a neutrino. But if you had something like WW production, where you had two neutrinos, it wouldn't work so well, because you couldn't reconstruct the neutrino transverse momentum, which you need. I should mention, I said before that you're using the neutrino momentum here, and you weren't in when you look at the lepton PT, right? But if all we're doing is setting the neutrino transverse momentum equal to minus the lepton transverse momentum, then you're not actually using anything. But really, when we talk about the neutrino transverse momentum, we're not setting it equal to minus the lepton momentum. We're setting it equal to minus the momentum of everything in the event. So you really have to measure the full transverse energy. So it depends on the whole radiation in the detector. And that's why it doesn't have to be equal. And nothing in this derivation assumed that the neutrino momentum was the opposite. I mean, in leading order it is, but when you measure it, it's not. And this distribution can be calculated at higher orders when other effects come in. So when you have two neutrinos, you measure the total transverse momentum, which could be 0, even though there's two hard neutrinos in the event, because they could say go back to back, and you wouldn't see any missing energy at all. So those cases are more complicated, but there's ways to also construct observables that have kinematical features. These are generally known as Razor variables. The simplest one is called MT2, which was developed for studying supersymmetric models. So the classic example is something like where we produce a slepton, which decays to, say, an electron and a neutralino and another slepton, which decays to, say, a positron and a neutralino. It doesn't really matter what these particles are. This is some charged particle that has some mass, and this neutralino is some other particle that's neutral, so you don't see it. It's stable and has some mass, and this is an electron. So in general, what we don't know in this is we don't know the mass of the neutralino, we don't know the mass of the chargino, and we don't know the transverse momentum separately of these two. But we do measure the total transverse momentum in the event, and so we can determine the sum of these. Right? But suppose we just had one of these, right? So one of these sectors looks a lot like a W, where this would be the W and that would be the neutrino. But we have to generalize transverse mass. Well, we don't really have to generalize it. If we put in the definition and use the neutrino mass, we would have the transverse mass is the mass of the neutralino plus the mass of the electron squared plus, and you can kind of simplify the formula for transverse mass. So let me just write it this way. PT E dot PT. Okay. This just comes from expanding that transverse mass. So this would be the transverse mass if we just had one side where we knew this was a neutrino and this was one neutralino and that was the lepton. So if we can measure this, we need to know the transverse energy and the transverse momentum of that neutralino to use it, and we don't. We only know the sum of them. And we also don't know this. This is unknown. So this is unknown, and this is unknown in practice. So what you can do instead is take something called MT2, which is defined as the minimum of MT, MT2 squared. Let me just write it as MT as a function of, so this is going to be a function of M chi. So you guess a value of M chi, and then you calculate this as a function of M chi and PT chi 1 and MT of the other section with the same neutralino mass but PT chi 2. Right, and you minimize this over PT chi 1 plus PT chi 2 is PT missing. Right? So we know the sum of, we know that we have a constraint that the sum of the momenta equal the missing momentum, but we don't know how to distribute it. So, but you can, for a given choice of partitioning of the missing transverse momentum into the two, you can calculate this for one half and calculate this for the other half, and then take the minimum. Right? And this seems like a very unusual thing to do. But it has the nice feature that it will, if you have the right value of M chi, then this will have an endpoint at the slepton mass. So we also don't know the slepton mass. So you think of this like the W, and this like the neutrino. Right? So what you'd like is that the variable to have an endpoint at the slepton mass, like MT2 had MT had an endpoint at the W mass. And this minimization procedure will have that feature. it's not obvious, but it's true, at the endpoint of this lepton mass if you get the right neutralino mass. But of course, you don't know the right neutralino mass, so if you just guess a random thing, it'll have a random endpoint, and you don't learn much at all. So then what you can do is you take what's called MT2 max, which is the the maximum of MT2 of M chi. So remember, each of these MT2 will be a distribution. If I choose a value of M chi, I can measure this, and I get a distribution for each value of M chi. So for that distribution, I'm going to max over events. So if I take all the events and take the maximum value it has, and I'm going to plot that maximum as a function of M chi. And what happens when you do that, you get this very interesting distribution. So this is M chi is over here. You find out that there's this weird feature. There's a kink. There's a singularity in the MT2 max distribution. And so it turns out what you can do is measure this distribution. So you calculate MT2 for all events, then you vary M chi, and then you plot that distribution, and you look for a kink. And by finding the location of the kink, you can determine M chi. And then using that value of M chi, you can look at the endpoint of the distribution to find this lepton mass. This is a really cool technique that you seem to get something for nothing by looking for these kinematical features. And there's an interesting way to do this analysis to understand why this kink appears from seeing that there's actually a multidimensional space projected onto a lower dimensional space that produces this singularity. I'm not going to derive it. I don't know of a simple derivation, but I can give you some references if you want. Anyway, this was really exciting. I don't know, 5 years ago or so. Experimentalists tried it. It didn't really work as well in practice. In practice, these kind of Razor variables like MT2 are used just as observables in certain contexts where you pick a mass and you look at the distribution and maybe look for an endpoint or use it to find signal versus background. This technique hasn't actually proved useful in experiments yet, but it's an interesting idea that's worth having in mind. Yeah, so they see the kink there? Yeah, that's a kink in this MT2 max. So that's the plot of MT2 max as a function of chi. Right? At the correct value. So what we're doing is simulating events with a given value of M chi, but I don't tell you what it is. I just simulate a billion events, and I give you the events, and then you do this processing, and then you try to figure out what the neutralino mass is and what the lepton mass is. Yeah, the correct mass, right? And what you're doing is, from the theory point of view, you're varying the mass, constructing the observable, which depends on the postulated mass. And as you vary it, you find there's a kink at the correct mass. It's really kind of cool, and there's generalizations of this technique that find application, but I don't know. These are called Razor variables. They're used a lot by CMS. But again, mostly they're used for signal background discrimination. But eventually, if we see some supersymmetry, they might be used to measure properties of it. Yeah? Yeah, it's M chi. I don't know why it's labeled like that. It didn't say it had to be the same as M chi. It's supposed to be the same as the lepton mass. So here, the lepton mass is 300. So that's where the endpoint is. Well, it's MT. Yeah, I mean, once you know the neutrino mass, you can calculate. I don't know. I think it's supposed to be MT2. Yeah, MT2. Yeah, the notation is a little different, but I took this part from the paper. But that's the idea. So the simulation was done with a lepton mass of 300 GeV and a neutralino mass of 100, and you can see the kink is precisely at the location of those. Anyway.
Small fraction of events are populated with blue. So in
only
practice, is it possible to see that?
No, in practice it's not, but it's a work in progress. I mean, again, this is assumed, we have infinite statistics on no backgrounds.
That's the parton level.
Yeah, these are right, but it's just leptons. So parton's okay.
That doesn't mean
No, people have tried it in WW, which is a similar scenario, and it didn't really work that well, precisely because the backgrounds are fairly large. Right? WW, where you might say, you look for an electron and a muon, maybe it's fairly clean, but still, they don't even have enough statistics of that to see these features. So it hasn't been used yet in data, but in principle, it could be. And for me, it's exciting that as a proof of principle that you can get something out of nothing, right? It seems like there's so many unknowns, but if you process the data enough, you can see it. In general, if you plot any distribution, it'll depend on both masses in some way, and you should be able to do a fit. But it's a nice way to simplify it, so you can see by eye where the variables are. Yeah.
So you simulate events with
Yeah. Right. Yes. Right. So that's each of these is this isn't a guess. This is the distribution, each vertical. So the guesses are along the horizontal axis. You're guessing a value of m chi. And then the colors here are the histograms. So there's a histogram in the distribution of events. Each of these are the same number of events. Right? They're all the same events, and each row uses the events over and over again. Right? And they all have an endpoint at something, but you see the location of the endpoint depends on the m chi. The true Slepton mass is over here, is 300, but you only get the true one if you have m chi correct, right? But you can figure out what the correct value is by looking for this cusp, right? That's the idea. Right now, it's mostly theorists that are using it, but eventually, maybe it can be useful experimentally. Okay, this will stop here, and next time we'll start talking about particles. Oh, I forgot jets.
Let me ask.
Yeah.
So